let's go ahead and start with a quick sound check. Let me see if I can hear myself. And yes, I can, so that's our sound check taken care of. Let me go ahead and unplug this headset, and then we can get started. Alright, that's my headset gone and taken care of. And no, we are not covering light and optics today. That's an AP Physics 2 subject, which I don't get to teach very often because AP Physics 2 isn't chosen by students very often. Instead, we're still sticking to AP Physics 1, or I guess you could also include AP Physics C Mechanics today. And just like last time, I've decided that I'm just going to go over some book problems that I assigned to one of my students. So this time the topic is going to be momentum, and if we finish going through the problems before the 2 hours are up, then I'm thinking of maybe exploring a certain idea in rotational dynamics that I didn't get to go over last time. I mentioned it last time. Well, I didn't mention exactly what it was, but I did mention that I might record a video on it, and I didn't really have the opportunity to do that this past week, so we'll see. But I really do want to cover it. I'm still not even sure what the result is going to be, but well, I'll talk about it later if I get the chance. But it's about a point of confusion where students aren't sure whether to use rotational kinetic energy and translational, or just rotational kinetic energy for certain scenarios. But we'll worry about that later. For now, I just want to go over some momentum questions first. So, without further ado, let us begin. First off, I want to do, it's problem number 20. From my book. So it says we have a rifle with a weight of 30 newtons, fires a 5-gram bullet. So a rifle with a weight of 30 newtons fires a 5-gram bullet. So mg equals 30 newtons, and the bullet that gets fired out of it is 5 grams, which is the same as 0.005 in kilograms. And it's fired out with a speed of 300 meters per second. 300 meters per second. Let's see. It says find the recoil speed of the rifle, that's part A, and then part B, if a 700 Newton man holds the rifle firmly against his shoulder, find the recoil speed of the man and rifle. Okay, so this is just a conservation of momentum problem. We know that momentum is conserved if the following condition is fulfilled. A lot of people skip over this condition, but it is a condition we need to check for. The net force external has to be 0. There have to be no external forces acting on the objects involved in the collision. I guess you could say this is a collision happening backwards in time. Two objects are separating rather than colliding with each other, but the same idea applies. So, what are the forces acting on these objects during the collision? Or, in this case, during the anti-collision, the separation? just the force that the gun exerts on the bullet, and the bullet will exert a reaction to that back on the gun. So the bullet gets pushed forward and the rifle gets pushed back. But those are not external forces. Those are forces exerted by the objects in the system on the objects in the system. In this case, our system is just the two objects, the rifle and the bullet. So any forces they exert on each other, those are fine. But no external forces are involved. There is no friction mentioned, no air resistance of any sort. There is normal force and gravity acting on the bullet when it's inside the rifle, but they cancel each other out. And I guess the force of gravity acting on the rifle itself is accounted for by the person carrying the rifle applying a force upward, so it doesn't accelerate up or down, so no net external force on the rifle. I guess gravity will start acting on the bullet after it's fired, but we're just talking about the split second when the bullet exits the rifle, so there isn't any time for gravity to have an influence yet. I know that might be overkill and we're thinking about it too hard, but I would rather do this than the alternative, which is forgetting that this condition must be met for momentum to be conserved, because I've seen a lot of students make mistakes where they just assume momentum is conserved just because. I've even heard people say momentum is always conserved, which is definitely not true. Anyway, let's go ahead and do some math. So I want to figure out the mass of the rifle here, and I guess I should have labeled it M rifle. So M rifle is equal to 30 newtons over G. 30 over G is 9.8, or 9.81 if that's what you prefer, or even 10 if you prefer to simplify it even further than that. But 30 over 9.8 gives me 3.06 kilograms. 3.06 kilograms, give or take. And again, for any of you who are new to the way I do things, I don't really care too much about significant figures. That's for chemistry. This is physics. In physics, we don't really nitpick over that. You can worry about your sig figs when you're working for NASA. Anyway, we've got the mass, so now what we should be able to do is just write our conservation of momentum equation. M rifle times V rifle plus M bullet times V bullet, and these are their final velocities, equals their initial momentum, which was 0 for the rifle and 0 for the bullet. Total momentum final equals total momentum initial. So that leaves us with, what can we substitute in? We've got 3.06 times V rifle is our unknown, plus 0.005 kilograms for the bullet times V bullet is 300 equals 0. Let's see, 0.005 times 300 is 1.5, and if we subtract 1.5 on both sides, we get 3.06 V rifle equals negative 1.5. Divide by 3.06, and I get V rifle equals negative 0.49 meters per second. Now, the negative sign means that it's going to, unsurprisingly, move in the opposite direction to where the bullet was fired. But the negative on its own doesn't automatically mean anything if we haven't defined what positive means. So on an answer sheet for a test, you wouldn't just report your answer like this. You would rewrite it as 0.49 meters per second backwards or towards the person firing the gun. And actually, it says find the recoil speed of the rifle, so even more reason not to keep the negative sign in your final answer, because it didn't ask for velocity, it asked for speed, magnitude only. Okay, so part B says if a 700 Newton man holds the rifle firmly against his shoulder, find the recoil speed of the man and rifle. So if we add, this is going to look very silly because of the proportions, but if we add someone over here to hold the rifle for us, that's not how people are supposed to carry their rifles, but that's the best I can do with my art skills. Actually, that looks really weird because I used the same color for the person and the rifle. Oh well. If this person has an MG of 700 newtons, then how does the problem change? What is the recoil speed of the man and rifle? So they said he holds the rifle firmly against his shoulder, which basically means that you can treat the man and rifle as a single combined object. So not much changes as far as our equations are concerned. There's still no net external force. There's the man's normal force against the back of the rifle, and the rifle exerts an equal amount of normal force back on the man. Those are internal forces. The momentum change due to those forces would cancel out between the man and the rifle, and since the man is now included in our system of man, rifle, and bullet, yeah, those forces are not external. So that leaves us with, let's see, we would write this equation again, but instead of M rifle and V rifle, it would be the mass of rifle and man times velocity of rifle and man. So this part doesn't change. This is still going to give us the 1.5, so we're still going to get negative 1.5 over here. Only difference is this part. So let's see. Go ahead and calculate the mass of the man. 700 over G is equal to, I'm getting 71.4 kilograms, which is fairly typical for an adult human. About 150-ish pounds, give or take. And let's see, 71.4, we're going to add that to the 3.06 from earlier, so that gives us 74.46 would be their combined mass. 74.46 is the mass of the man and rifle times the velocity of the man and rifle equals the negative 1.5 that we got from M bullet V bullet the last time around. And the rest plays out pretty much the same. Just divide and we're all but done. Negative 1.5 over 74.46 gives me negative 0.02. V, man, and rifle. Probably should have come up with simpler names for these variables. Equals negative 0.02. And I guess if I want another digit, the next digit is still a 0. Negative 0.020 meters per second. And again, since it's asking for speed, I would drop the negative and just report my final answer as 0.02 meters per second, which is quite the dramatic change from the negative 0.49 we had earlier. This is the reason why when you fire a rifle, you should hold it firmly against your shoulder. Because if you hold it the way I drew it over here, then what's going to happen is the bullet gets fired and then the rifle gets launched backwards and it bumps right into the person, and that's probably going to result in an injury. Whereas if the person is already holding it firmly against their shoulder, then that doesn't happen because they move together at a slower speed. So that takes care of number 20. Next is number 22. Not that these numbers mean much to you guys since you don't see my book pages, but for those of you who are my students and have been given those pages to look at, you know what I'm referring to. Number 22 says a 65 kilogram person throws a 0.045 kilogram snowball forward with a ground speed of 30 meters per second. A second person with a mass of 60 kilograms catches the snowball. So let's go ahead and start drawing up what we have. So 65 kilogram person holding a snowball. Sometime later, they have thrown the snowball. Towards, let's see, a second person with a mass of 60 kilograms. So here's our 65 kilogram person. I guess we'll redraw the 60 kilogram person over here. And here is their 60 kilograms again. Is that visible on the screen? Yes, it is. I have to keep double checking that because I know I keep on shifting the position of my paper. Anyway, where were we? So that's scene 2, I guess, and then scene 3 is our 65 kilogram person is still doing whatever they were doing after throwing the snowball, and the snowball gets caught by the 60 kilogram person, at least I'm assuming. I haven't finished reading the problem yet. Let's see. So a second person with a mass of 60 kilograms catches the snowball. Yep, I guessed correctly. Both people are on skates. This implies that you should assume they're moving with no friction along the surface that they're standing on. The first person is initially moving forward with a speed of 2.5 meters per second, and the second person is initially at rest. What are the velocities of the two people after the snowball is exchanged? Disregard friction between the skates and the ice. Okay, so 65 kilogram person is moving at 2.5 meters per second at first. Forward. The second person is initially at rest. And then they said the snowball, which is 0.045 kilograms, so mass of the snowball, I'll just call it M snow, is 0.045 kilograms. It gets thrown with, what did they say? Gets thrown forward with a ground speed of 30 meters per second. That's 30 meters per second relative to the ground. In fact, all of the speeds that were given here are relative to the ground, which is good because then we don't have to add or subtract any of our velocities to figure out what their true ground velocity is. Let's see. And what are the velocities of the two people after the snowball is exchanged? Okay, so I can go ahead and do this in 2 steps. The step between these 2 scenes and then the step between these 2 scenes. So step 1, we can figure out the final velocity of the person who threw the snowball, and they did ask for velocities, so direction needs to be included in our final answer. 65 kilogram person with well, let's see. So first of all, forces over here. Is our net force external equal to 0? Technically, no, because gravity is going to affect the snowball while it's transitioning between person 1 and person 2, but we will neglect that effect. Actually, no, we don't even have to neglect it. We can say that the momentum is conserved in the horizontal direction, but not in the vertical. Yeah, we can do that. There's no net external force horizontally. Vertically, gravity is going to have an effect which is probably not going to be all that significant. If the snowball gets thrown from a short enough distance that the other person can catch it before it hits the ground, then it's not going to be that big of a deal. But in any case, even if it was, we're focusing solely on the horizontal momentum here. So, yeah. Forces exerted horizontally would be the person pushing on the snowball forward, so I guess you could call it an applied force, although I would be more specific and call it a normal force, because applied force is not really a force. But you can call it applied force if that's easier for you, and then the reaction to that force pushes back on the person. Those are internal forces. They exist between the 2 objects that are colliding and or separating. So that's perfectly fine to have. And I can't think of any other possible external forces. Air resistance isn't here, friction isn't here. We're told to consider those to be negligible, or at least we can reasonably assume that they're negligible. And yeah, I think we're good to go with our conservation of momentum equation. So, how do I want to label the masses of these people? I'll call this one M1, and I'll call this second person M2. And then I'm going to go M1 V1 initial plus M snow V snow initial. And I guess I could include the second person, but if I'm just looking between these 2 scenes, the second person isn't involved in that first step. If I include him, he'll just be canceled out. Let's go ahead and do that just for the sake of illustration. Plus m2 v2 initial equals m1 v1 final plus m snow. Whoops, snow, not smo. V snow final plus m2 v2 final. Let's see. So actually, this isn't even v snow final. Final isn't the right name for it, but that's the name I'll stick with for now. Actually, you know what? I'm going to call it v air. Yeah, v snow air while it's in the air before it gets caught by the second person. So yeah, whatever v2 initial is, it doesn't even matter. I mean, we know it's 0 because person 2 is initially at rest. And come to think of it, calling their speed over here v2 final is also not the best of ideas. Oh well, you know what it means. You know what I mean by it. So anyway, there's no change in the speed of person 2 because there's no collision happening with person 2 yet. So it doesn't matter even if you include him or her in the system. Let's go ahead and plug in the numbers that we know. We know that this person is 65 kilograms, initially moving at 2.5 meters per second. We know the snowball is 0.045 kilograms, initially moving at 2.5. A lot of people get this wrong and they assume the snowball is at rest. The snowball is only at rest relative to the person carrying it. But relative to the ground, relative to if you were standing and watching this happen, the snowball from your perspective is moving just as fast as the person carrying it. So it's moving at 2.5 meters per second. And then plus nothing, we don't need that third term. And then equals m1 v1 final, so 65 times we don't know yet, plus 0.045 times, now we know it's 30 meters per second, and we don't need that third term. Okay, so only one unknown here. Let's solve for it. I'm going to subtract whatever 0.045 times 30 is from that sum. So we've got 65 times 2.5 plus 0.045 times 2.5. And yes, I could have factored out the 2.5 and just done 65.045 times 2.5. But, you know, if you don't see that immediately, no shame in doing it step by step like this. And then, where were we? Subtract 0.045 times 30. Okay, so that's what I've got. 161.2625 equals, it's going to be 65 times V1 final, so 161.2625 equals 65 V1 final. Divide by 65, and I'm getting 2.48. 2.48. V1 final, I guess I'll write it over here. V1 final equals 2.48 meters per second. So they were initially moving at 2.5 and they got slowed down just a little bit from throwing a snowball, which isn't surprising considering how little mass the snowball has compared to the person, we shouldn't expect that much of a change in their velocity. And it's also then not very surprising that the direction of their velocity is still forward. After all, this came out positive. Okay, next up is part... Actually, it's not even divided into a part A and a part B. It's just asking both questions. So the second question is... Or actually, no, it's all one question. What are the velocities of the two people after the snowball is exchanged? They could have done that as two questions, but whatever. Still two things to solve for at the end of the day, no matter how many questions they break it into. Or don't break it into in this case. So now I want to do the exchange between the snowball and the second person. So we've got m snow times v snow in the air. Specifically just the x component of it, because we mentioned we're just doing conservation of momentum in the x direction, so don't bother with calculating the y component of its velocity, plus, well, initially the second person was at rest, so plus 0 equals m snow v snow final, for real this time, m snow, why did I put a comma there, m snow v snow final plus m2 v2 final. And this time I really mean it when I say final. Anyway, subbing in the numbers that we know, we have 0.045 times 30 equals 0.045 times v snow final plus 60 times v final. Well, when the person catches the snowball, they both have the same v final, so in fact I can factor out the v final for both of them. V snow final equals v2 final. So I can factor out, I'll just call it v2 final since it's quicker to write. I'll factor that out for both of them, like so. And this shouldn't be too hard. 0.045 times 30 is 1.35 equals that whole thing. So if I divide by, that's going to be 60.045. If I divide by 60.045, I get v2 final is 0.022, I guess I'll round it to 5, 0.0225. v2 final is positive 0.0225. The fact that it's positive should not be surprising. If you started with a snowball whose momentum was to the right plus a person whose momentum was 0, then your total momentum was to the right before the collision. It better still be to the right after the collision. The direction of the total momentum has to be the same before and after. And there we go. So that's pretty much it. And it's not that much of a surprise that it's so small because, again, really small mass on the snowball doesn't carry that much momentum, and then if you're then going to share it with a 60 kilogram person, spreading all that out over a mass of 60 kilograms isn't going to result in very much speed. Okay, anything else with this problem before we move on? It doesn't look like it says anything else. Okay, next up I had 24 through 26. 24 24 through 26. So 24 says, two ice skaters are holding hands at the center of a frozen pond when an argument ensues. Skater A shoves Skater B along a horizontal direction. Identify, Part A, the horizontal forces acting on Skater A. Part B, the horizontal forces acting on Skater B. And then Part C, which force is greater, the force on A or the force on B. And Part D, can conservation of momentum be used for the system of A and B? Defend your answer. And then Part E, if A has a mass of 0.9 times that of B and B begins to move away with a speed of 2 meters per second, find the speed of A. I know that was a mouthful, and I will reread it as we progress through one part at a time, but let's just go through it step by step. Which color do I want to use? I feel like I haven't used this one. Wait a minute. Yes, I did. I guess we can go back to, what is this? I think it's navy blue. It probably looks black to most people, though. Let's see. So, two ice skaters, Skater A and Skater B. They're standing next to each other on a frozen pond initially. Sometime later, Skater A pushes Skater B, and they start to separate. So I'll call this VA, and I'll call this VB, not drawn to scale because we don't even know what their final velocities are going to be yet. So, it says for Part A, identify the horizontal forces acting on Skater A, and for Part B, identify the horizontal forces acting on Skater B. If they are on a frozen pond, and if we assume that the ice has negligible friction, then the only horizontal forces acting on them during that initial push would be the force applied by A onto B, which is really a normal force, but we'll call it an applied force, and the reaction is the force applied by B on A. And that's it. That answers parts A and B, actually. Part C, which force is greater, the force on A or the force on B? I mean, I pretty much gave it away. If we're applying Newton's third law here to get this other applied force that's acting on person A who initially decides to push, then we already know what Newton's third law says. These forces are opposite in direction but equal in magnitude, so neither is greater. They both have the same amount of force acting on them. Part D, can conservation of momentum be used for the system of A and B? Defend your answer. Can it be used? Well, what have I said for the past two problems? The condition for conservation of momentum is that the net force external must be 0. And over here, if we consider our system to be these two skaters, then the only forces acting on them, at least in the horizontal direction, are the forces that they exert on each other. So yes, momentum is conserved. As for vertically their momentum is conserved as well, because over here the normal force cancels with the weight for each skater. Not that we were worried about momentum conservation in the vertical direction anyway, but just some extra information in case you encounter a problem where it does matter. Let's see. We just did part D. Part E, if A has a mass of 0.9 times that of B, and B begins to move away with a speed of 2 meters per second, find the speed of A. So, if mass of A equals 0.9 times the mass of B, so B is the bigger person, and B begins to move away with a speed of 2 meters per second. VB equals 2 meters per second. Let me wall that off. Then find the speed of A. Speed, that means we need to get the magnitude, but we still want to see a negative sign because we know that this person is going to have to move in the opposite direction if they both started from rest. If we don't see a negative sign, then that tells us we did something wrong with our math. So even though we don't want the negative sign in the end, we still want to see it before the end, just to make sure we did everything right. I mean, even if we do get it, it doesn't guarantee we did everything right, but, you know, it's one of those things where if it's missing, you know something went wrong, which is better than nothing, I guess. It's always good to have some sort of indication that you can look at that will tell you if something went wrong with your math and that you need to double check it. Anyway, why am I holding my calculator? We're not ready for that step yet. So we can do initial momentum equals final momentum. So initial momentum is 0 before one of them pushes the other. So their initial momentum is 0 for the first person plus 0 for the second, equals MAVA plus MBVB. Okay, and I'm just going to rewrite MA in terms of MB. So 0 equals MA, which is going to be 0.9 MB times VA plus MB times VB was 2. Okay, I can divide both sides by MB. 0 divided by MB is still 0, and if I divide the right-hand side by MB, then the MB cancels out. I'm going to subtract 0.9 VA on... Actually, no, I'm going to subtract 2 on both sides, so I get negative 2 equals 0.9 VA. And divide by 0.9. Negative 2 divided by 0.9 is negative 2.22, repeating. So VA equals negative 2.22 meters per second, and therefore the speed is 2.22 without the negative sign. And we're done. And I think this marker is almost done too. It's starting to fade. All right, that takes care of number 24. What does 25 say? An archer shoots an arrow toward a 300-gram target that is sliding in her direction at a speed of 2.5 meters per second. Okay, so it's an initially moving target. A lot of people will not pick up on that. Be very careful when reading your problems. Let's see. I'll just reread it from the start because I've lost my place. An archer shoots an arrow toward a 300-gram target that is sliding in her direction at a speed of 2.5 meters per second on a smooth, slippery surface. The 22.5 gram arrow is shot with a speed of 35 meters per second and passes through the target, which is stopped by the impact. What is the speed of the arrow after passing through the target? Okay, somewhat of an improvised ballistic pendulum, kind of. So let's see, which direction? The mass of the target is given in grams, and the mass of the arrow is given in grams. So this time, actually, I don't think I need to convert to kilograms, because I'm pretty sure the grams are just going to end up canceling out. So the target was sliding in the archer's direction. So the archer isn't really a part of this collision, which is probably why they did not mention her mass. The arrow is moving towards the target, and the target is also moving towards the arrow. So the arrow is moving towards the target. They said the arrow is shot with a speed of 35 meters per second. And the target is sliding towards the archer and therefore towards the arrow at 2.5 meters per second, or negative 2.5 if you want this to be a velocity instead of a speed. If we're only working in one dimension, then using a simple negative sign can help indicate that you're moving to the left. Anyway, let's see. So they say that the target gets stopped by the impact. What is the speed of the arrow after it passes through the target? So sometime later, the target is punctured. I guess I'll draw it down here. Sometime later, the target is just going to have, I guess I'll draw something like it got torn up and messed up. I don't even know how to illustrate that, but target got punctured, the arrow went straight through it. The target comes to a complete stop. What is V arrow final? I'll call it V A final. Okay, let me write down the other details first. So the target was 300 grams. The arrow was 22.5 grams. And that should be all the information we need. So let's go ahead and justify the use of conservation of momentum. During the collision, is the net force external 0? What forces are acting on the arrow and the target? Well, when they collide, I guess we'll call it an applied force, but really it's, again, a normal force. When two things press against each other, that's always a normal force. Usually, the applied force is just a convenient name that we give to a normal force or a friction force or a tension force, but perhaps you're already tired of me yammering on about the applied force not being a real type of force, so we'll call it applied force again, even though I don't like it. And yeah, during the collision, whatever force the arrow applies on the target applies that same amount of force back on the arrow until they separate. So they're applying the same amount of force on each other for the same amount of time, which results in the same change in momentum. So whatever momentum change happens to the target, an equal and opposite amount of momentum change happens to the arrow. So the total momentum across target and arrow is unchanged. Though their individual momenta will change, their combined momentum does not. Their total is still the same. Gravity might factor into this if we were considering momentum in 2 dimensions, but we're just going to consider it in 1 dimension in the horizontal direction, so we can ignore the effects of gravity on the arrow. For the y component, we don't have to worry about it, but in the x direction, momentum is most certainly conserved. So we can do mass arrow v arrow initial plus mass target v target initial. Did I use a capital A or a lowercase a is what I used earlier, so let me be consistent. Plus mass target v target initial equals mass arrow v arrow final plus mass target v target final. Well, we know this is 0. The target comes to rest. And yeah, we can just fill in the rest with the numbers we already have. So mass of the arrow, 22.5 grams. I'm writing the units in just so that we can show that they're going to cancel out. Times v arrow initial is 35 meters per second plus mass of the target is 300 grams times negative 2.5 meters per second. Don't forget that the target is moving in the exact opposite direction. And then equals, that's going to be 22.5 grams times whatever v arrow final is. So yeah, even if I converted everything to kilograms, I'd be dividing this by 1,000 and dividing this by 1,000 and dividing this by 1,000. Dividing by 1,000 on both sides of the equation ultimately changes nothing. So yeah, you could also just cancel the grams on both sides of the equation, and there you go. The units don't matter as long as they're consistent with each other. If one of them was in grams and the other was in kilograms, then yeah, you would have problems. But if they're all in the same units, then that's fine. The units will cancel out, and since these are both in meters per second, this VA final should still come out in meters per second. So 22.5 times 35 plus, or rather minus 300 times 2.5. Wait, 300? Yeah, 300 is negative 727.5. Wait, really? Oh. Does that mean the arrow doesn't... Hold on. That can't be right, is it? Hold on. Oh, I forgot to multiply by 35. I knew something was off. 22.5 times 35. There we go. Minus 300 times 2.5. 37.5. That's much better. Because I was about to say, if that's negative, then that meant that... Then that would... The only thing that could possibly happen is for the arrow to bounce off the target and go back to the left, and that didn't sound right. Okay, so I'm getting 37.5. Is that visible on the screen? Yes, it is. Equals 22.5 V final So dividing by 22.5, I get 1.67. V final is positive 1.67 meters per second. Does it make sense? Well, it's still to the right, which is consistent with what we were told, that the arrow just pierces through the target. So it makes sense that it's positive and to the right. And it is smaller than it was initially, which also makes sense. It should have been slowed down by some considerable amount, considering that not only did it have to go through the target in the first place, but it had to go through a target that was moving towards it. So yeah, I'm not surprised by a great loss in speed. And yeah, I think that's all the commentary I can offer on this problem. Did they say... Well, they said, what's the speed of the arrow after passing through the target? If it had to be negative, we would drop the negative sign because it asked for speed and not velocity, but there you go, that's the result. Okay, next one. We have 26 says, a 75 kilogram ice skater moving at 10 meters per second crashes into a stationary skater of equal mass. After the collision, the two skaters move as a unit at 5 meters per second. Okay, that's what we are supposed to get when we do the math. Suppose the average force a skater can experience without breaking a bone is 4,500 newtons. If the impact time is 0.1 seconds, does a bone break? Okay, so this one is less about applying conservation of momentum and more about just figuring out how much force was involved in the collision. How much force was in this impact? So we've got mass is 75 kilograms for each skater. We only have to look at one skater because whatever force is applied to one skater, the same amount must have applied to the other one. Their V initial, I'm just going to look at the original skater. V initial is 10 meters per second. V final is 5 meters per second. Is it still in the same direction? I mean, it better be. If the other skater was stationary, then yeah, there should be no change in direction. If the total momentum was to the, let's say, right, and the other person wasn't moving, then yeah, the total should still be to the right after collision. No change in direction there, which is actually good, because if there was a change in direction, that would increase the force in the collision and thereby increase the likelihood of bones breaking. And we definitely don't want that. So I guess let's go ahead and calculate. We were given that the time of the collision was 0.1 seconds. So let's figure out how much force was in this collision and compare it to, they said, 4,500 newtons is the maximum force beyond which bones start breaking. So let's go ahead and calculate the change in this person's momentum. It is going to be mv final plus mv initial, or sorry, minus mv initial. We can factor out the m if we want, and then we can do 75 kilograms times v final minus v initial, or delta v. 5 minus 10 is -5. The negative just means that the force is opposite to the direction that the person was initially moving, which is exactly what we would expect. If someone gets slowed down, they must have been pushed opposite to the direction they were originally moving. So 75 times negative 5, what is that? 375, I think? Negative 375? Yep. Negative 375 kilogram meters per second. And we can set the change in momentum equal to the impulse. The impulse momentum theorem tells us that impulse is equal to change in momentum. So if the impulse is negative 375, then we can also set that equal to the definition of impulse. Impulse is equal to force times change in time. So negative 375 is equal to force times 0.1 divide by 0.1, which is the same as multiplying by 10, and the force is negative 3750. The negative meaning that the force is opposite to the direction of motion. The magnitude of the force, 3750, is less than 4500, so no, a bone does not break. And that takes care of number 26. Next up, I have number 28, which says, a 7-gram bullet is fired into a 1.5 kilogram ballistic pendulum. The bullet emerges from the block with a speed of 200 meters per second, and the block rises to a maximum height of 12 centimeters. Find the initial speed of the bullet. Let's see if I can fit that stuff on this page. Don't want to waste paper after all. 7-gram bullet fired into a 1.5 kilogram ballistic pendulum. So, bullet fired into a block. Sometime later, the block rises. And does the bullet stay inside or does it pass through? Let's see. The bullet emerges from the block with a speed of 200 meters per second. So the bullet, I guess what they're implying then is that the bullet pierced through without rising with the block. Yeah, I wish they could have worded this problem a little bit more clearly. You have to make a little bit of an assumption and do a little bit of mind reading to understand what the author of the book meant for you to do with this problem. But I think it would be too complicated if you assumed that the bullet stayed inside the block before emerging, especially given how fast bullets move. I would think the bullet would escape the block before the block rises to any significant degree. And I guess I need to draw like a hole burrowed through the block where the bullet passed through. And yeah, that's our before and after picture. So, actually, what I probably should have drawn is like a middle picture where the bullet comes out and the block still hasn't risen. But we'll work with this. So, 7-gram bullet. We know that the bullet is 7 grams. Well, let's see. Bullet and block both start with the letter B, so I don't want to use a single letter here unless I can come up with a different name. I guess we can refer to the bullet as a shell, and for the block, since it's made out of presumably wood, I'm just going to assume the block is made out of wood, and I will label it with a W. So yeah, for the bullet I will use S, and for the block I will use W. So MS, the mass of the shell, is going to be 7 grams, which is 0.007 if I convert it to kilograms. The mass of the wood block, MW, is, was it 1.5? Yeah, 1.5 kilograms. The bullet emerges from the block with a speed of 200 meters per second, so emerges with 200 meters per second. And the block rises to a maximum height of 12 centimeters. Let's use a different color for this. So rises by 12 centimeters. Find the initial speed of the bullet. So we've got 2 steps here. We've got a collision step and a conservation of energy step. Let's go ahead and look at our collision step first. During the collision, is our net force external 0? Well, I don't see any air resistance acting, at least horizontally, on the bullet or the block. There was no mention of it, so we can assume it's negligible. The only forces would be the force exerted by the bullet on the block and by the block onto the bullet. So that force, the force of the bullet on the block, has the effect of accelerating the block and giving it enough speed to rise, while the effect of the block on the bullet is to slow it down from whatever its original speed was. If it came out at 200 meters per second, then it must have gone in at something notably higher. So yeah, equal and opposite forces there, both of which are internal forces, and those aren't going to cause any change in momentum. I know it's probably sounding repetitive at this point, but I need to emphasize it. Make sure that your net force external is equal to 0. Just think through it for a few seconds before jumping to the conclusion that momentum is conserved. So our net force external equals 0. I can't see any reason for that not to be the case. There's probably a force of gravity, well, not probably, there's definitely a force of gravity that acts on the bullet, but it's only going to affect the vertical momentum and not the horizontal. So as far as, maybe I should call it net force external in the x direction to be more specific. Maybe that's what I should have done with most of the previous problems as well, but you get the idea by this point. Where was I? So, yeah, we just defined using conservation of momentum, so let's go ahead and write a momentum conservation equation. So it's going to be for just before the collision and just after the bullet emerges. I'm assuming the bullet emerges before the block has enough time to start rising. So I'm going to say M shell V shell initial plus M wood V wood initial, which is 0, equals M shell V shell final, which is 200, plus M wood V wood, I'm going to call it V wood bottom, B-O-T, bottom, and then its velocity is going to go to 0 when it rises, but that's for a separate equation. So what can we plug in here? I guess we can plug in the mass of the block and the mass of the bullet, and that's as far as we go. So 0.007 times V shell initial equals 0.007 times 200 plus 1.5 times V wood bottom. We still don't know what that is yet, but that's okay. We continue. Now we want to do conservation of energy for the wood block between the bottom, just after the bullet emerges from it, until it rises to its maximum height of 12 centimeters. Is energy conserved for the block? That's another thing that we need to check. Don't just assume it's conserved. What's the condition for conservation of energy? The non-conservative work has to be 0. Is it 0? Well, let's see. Forces acting on the block. We've got the force of gravity, which is conservative, so by definition, the non-conservative work due to gravity is 0. And then the other force would be the tension of the rope that's holding the ballistic pendulum. And for the tension in the rope, while it's not 0, it doesn't do any work, because as the block swings, the direction of the tension force is always parallel to the rope, and as the block swings, the rope always moves such that it's always perpendicular to the direction of motion, and therefore perpendicular to the direction of displacement. At the very beginning, the tension is straight up and the displacement starts off to the right. Then a little bit later, maybe the tension is up and to the left a little bit, and the displacement is up and to the right at a perfect 90-degree angle. So whatever the force of tension is while the block is swinging up, it's always perpendicular to the displacement at any given moment, which means the work done by it is 0. And those are the only forces here, so yes, our total non-conservative work is indeed 0, which means we can use conservation of energy. So let's see here. I want to do 1/2 times the mass of the wood block times V wood bottom squared, plus I'm going to set the potential energy to 0 at that height, equals the kinetic energy once it rises 12 centimeters should be 0, because that's the point, it's supposed to stop up there, plus mgh, which is going to be mw times g times h is going to be 12 centimeters or 0.12 in meters. The mass of the wood block doesn't even matter here. And I can multiply the 2 over, so I get V wood bottom squared is equal to 2 times 9.8 times the 0.12 from earlier, and then if I take the square root of that, square root of 2 times 9.8 times 0.12 is 1.53. I don't need to consider the negative root here because I'm just looking for the speed. I'm just looking for magnitude. So magnitude of VW bottom is equal to 1.53 meters per second. All right. Next up, we can plug this in over here. So we can get, let's see, 0.007 V shell initial equals 0.07 times 200 is 1.4, and then plus 1.5 times 1.53. So 1.5 times 1.53 is 2.295, plus 1.4 is 3.695, and then 3.695 divided by 0.007 is a whopping 527 point, I'm going to round that to 86 meters per second. That was the initial speed of the bullet when it first collided with the block. Yeah, that's a lot. I was expecting something closer to like 300, 350. But I can't see anything that could have gone wrong with our math. I mean, it's not completely outside the realm of possibility. Let me double check just to make sure. Did I convert correctly? Was it, let's see. Yeah, it was 7 grams, so 0.007 in kilograms. Nothing is wrong there. Did I calculate this right? 0.007 times 200. I did that one in my head, but let's double check with the calculator. Yeah, it's 1.4, so nothing wrong there. Okay, the only other possibility is maybe the author did want you to assume that the bullet rises with the block, in which case you would have to take it into account over here, but no, actually that would be way too complicated for what should be a simple high school physics problem. No, I don't think they would do that to you, because then you would have to consider you wouldn't be able to consider the bullet and block as a single object during the time that they're rising, because their kinetic energies are going to be separate. The bullet wouldn't be moving at the same speed as the block if it was still in the block while the block was rising. So I do think that the assumption we went with here is actually what the author of the problem intended. But it's good stuff to think about. Okay, I'm going to leave it at that, and if I have a realization later, then maybe I'll comment on it. But for now, I'm just going to go ahead and say that this is correct, because I don't see anything obvious that could have gone wrong, even though it does feel a little bit too high. Anyway, number 29 is next, and then after that, if we have time, I might look into something else, and it looks like we might. It looks like we might have time, but I guess it depends on what 29 is like. So 29 says, a .03 kilogram bullet is fired vertically at 200 meters per second into a .15 kilogram baseball that is initially at rest. How high does the combined bullet and baseball rise after the collision, assuming the bullet embeds itself in the ball? Okay, so a bullet is fired vertically into a baseball, and I guess if I want to draw a more accurate baseball, I need to put the little stitches on it. Where did the problem go? A 0.03 kilogram bullet is fired vertically at 200 meters per second into a 0.15 kilogram baseball. So 0.03 kilograms versus, where did it go? 0.15 kilograms. Not too much of a mass difference here. And it's fired vertically at 200 meters per second. This thing goes at 200 meters per second. How high does the combined bullet and baseball rise after the collision, assuming the bullet embeds itself in the ball? Okay, so for this problem, technically there is a net external force. Technically our net force external is not 0. However, it simplifies our calculations if we just go ahead and assume that the collision happens in such a brief period of time that the external force, which in this case is going to be gravity, over here we're dealing with vertical momentum since all the motion is vertical. If we assume that the force of gravity doesn't have enough time to alter the total momentum by very much during the collision, which is a pretty good assumption considering that the bullet is moving in at 200 meters per second. It happens almost instantaneously. We can then assume that the momentum is temporarily conserved while the bullet embeds itself in the baseball, and then from that point on, momentum is no longer conserved while energy is. So technically, net force external is not 0 here, and we shouldn't be using conservation of momentum, but if there isn't too much time between the bullet being launched and it lodging itself inside the baseball, then we can get away with it. There would be an error in our calculations, but it would be negligibly small. So, all that being said, let's go ahead and say that M... What should I go with this time? I think this time I'm going to go with... Actually, I'm just going to go with M1 and M2. I'm going to say that the bullet is M1 and the baseball is M2. So M1 V1 initial plus M2 V2 initial equals M1 V final plus M2 V final, where V final is the same for both objects. M2 V2 initial is 0. The baseball should be at rest. And then M1 V1 initial is going to be 0.03 times the 200 meters per second at which it was launched, equals, I can factor out V final, M1 plus M2, 0.15 plus 0.03 is 0.18, and then all that times V final. I guess I should write over here that this is equal to M1 plus M2 all times V final. That's where the 0.18 is coming from. It's just the M1 plus M2. Anyway, if I divide by 0.18, let's see, 0.03 times 200 divided by 0.18, I'm getting 33.33. So V final, actually I should probably call it V bottom, but V final equals, I'm getting 33.33 meters per second. And that's just after the collision. Then the ball and bullet rise together. And the question is, how high do they go? So from here, we can apply conservation of energy, because the only force acting on the bullet and baseball combination is the force of gravity, which is conservative. So the non-conservative work is 0. Work non-conservative is 0 because there are no non-conservative forces here. They didn't mention air resistance, and even if they did, you don't get taught how to deal with air resistance except in a very simple and extreme case. And I think that was the sound of my Kindle Fire begging to be plugged into a charger. Let me actually go and do that real quick. Alright, and that is done. Where was I? Oh, right, we're doing the energy part of the problem. So, our non-conservative work is 0, so we can say that, well, I guess I should draw some sort of unknown height that gets reached by this ball. I'm going to say that the height is 0 where the baseball originally started. That'll be my 0 of potential energy. So I'm going to do 1/2 times the total mass of M1 and M2. 1/2 M1 plus M2 times, I guess I called it V final squared, but now I'm going to rename it to V bottom squared, plus 0 potential energy equals mgh, M1 plus M2 times gh, plus 0 kinetic energy. It should have 0 kinetic energy at the top. If it's left with any kinetic energy, then it didn't rise as high as it could, now did it? So assume the kinetic energy is 0 by the time you reach the top. And that's an assumption that you can't make if there's some rotation involved. If it's still rotating in the air, then some of the kinetic energy stays in the rotational form and can't be converted into height. But that we might look at if we dig into a problem that a student sent me the other night. More on that in a minute, probably. The mass cancels out, so that part is taken care of. Multiply by 2 to get rid of the fraction, and we already know what V bottom is. So 2g and then h. And let's see. Actually, why did I do that? I need to divide by the 2g anyway. We're solving for h, not for v. My bad. So that's going to be v bottom squared over 2g equals 33.33 squared over 19.6, which is 33.33 squared over 19.6 is 56.678. I'm going to say 56.68. 56.68 meters. And I don't even have enough space to circle it, do I? Just barely. All right, that takes care of all the momentum problems that I had ready. So now the question is, do I dig into some of those other rotational dynamics questions here, or do I save those for separate videos? And also, the other question is, if I'm not going to do that, what will I do instead? Maybe look at some more of these momentum questions? You know what? In the interest of staying on theme, yeah, I think I'll just continue with momentum for today. We might have time to squeeze in 2 more problems. Let me see if I can pick some good ones out of here. Actually, here's one. We haven't dealt with anything involving relative velocity yet. Well, we kind of touched on it with one of the problems. The one with the snowball being thrown between 2 people. But here's one that looks like it might require a little bit more thinking than the snowball one. So it says, a 45 kilogram girl is standing on a 150 kilogram plank. The plank, originally at rest, is free to slide on a frozen lake, which is a flat, frictionless surface. The girl begins to walk along the plank at a constant velocity of 1.5 meters per second to the right, relative to the plank. Relative to the plank. So I guess I'll draw the after picture. So girl is moving to the right. The plank would have to move to the left if momentum is to be conserved. And they didn't say how fast the girl was actually moving from the perspective of an outside observer. They said she was moving at 1.5 meters per second relative to the plank. What that means is v girl relative to the plank. What that really means is v girl minus v plank. Or I guess v girl relative to the ground minus v plank relative to the ground. Relative velocity is the difference in velocity. If you're moving at, for example, 4 meters per second and there's a person behind you that's chasing you at 3 meters per second, then from their perspective you're moving at 1 meter per second, or from your perspective they're falling behind you at 1 meter per second. That's basically the idea that's at play here. So, it says, what is her velocity relative to the surface of the ice? And what is the velocity of the plank relative to the surface of the ice? Well, we already know that the difference between the two is 1.5 meters per second. And we can apply conservation of momentum to help fill in the gaps. So let's see what we can do here. First of all, we need to justify using conservation of momentum. Net force external, is it 0? Well, we're talking purely about horizontal momentum here, so we don't have to worry about the vertical forces. Horizontally, the forces would be just forces of friction between the girl's foot and the plank. Whatever friction the girl exerts on the plank to the left, an equal amount of friction is what pushes the girl to the right. And those are internal forces. Those are just forces that the two objects in this case exert on each other. So yeah, no other horizontal forces. So net external force is 0. The only horizontal forces here are forces that the objects exert on each other. Okay, then we can say m girl v girl initial, which is 0, plus m plank v plank initial, which is also 0, equals 45 times, I'll just call it v v girl relative to the ground. I'll just call it v girl, comma g, plus the plank was 150 kilograms times v plank relative to the ground. V plank relative to the ground. Okay, so what I can do is I can combine it with this equation over here. Since I've got two unknowns here, I need a second equation, and my second equation is the fact that their relative velocity is 1.5. So I can say v girl relative to the ground minus v plank relative to the ground is equal to 1.5, and now I've got my second equation. Let's see, do I want to use elimination or substitution in this case? If I multiply throughout by 150, I guess I could use elimination. Yeah, let's go ahead. We rarely get to use elimination anyway. Might as well take the opportunity. So I'm going to multiply everything by 150. So that gives me 225 equals 150 v girl relative to the ground minus 150 v plank relative to the ground. Minus 150 and plus 150 cancel out. 45 plus 150 is 195, and then 0 plus 225. So 225 equals 195 v girl relative to the ground, and divide by 195. 225 divided by 195 is 1.15 meters per second. So v girl relative to the ground is 1.15 meters per second. It does make sense that it's less than 1.5 because we know the plank is moving backwards. if the Planck was moving forward, then in order for her to have a 1.5 meter per second advantage over the Planck, she'd have to be moving faster than 1.5. But since the Planck is moving backwards, it implies that she doesn't have to be as fast to look like she's moving at 1.5 meters per second from the Planck's perspective. So yeah, we can go ahead and plug in this result over here, and what will that give us? 1.5 equals 1.15 minus v Planck. 1.5 minus 1.15 would be 0.35, so negative 0.35. v Planck relative to the ground is negative 0.35 meters per second. And there we go. That's a momentum problem involving relative velocity. Now, there is another formula that you could use for these relative velocity problems involving the center of mass of the system, but most students who are doing momentum have not yet learned the concept of center of mass, and even after you learn it, you can do just fine without it, so there isn't really much reason to trouble yourself learning a whole nother way of solving it when our current methods work just fine. It's mostly just a sort of shortcut formula, which I guess might be helpful if you're preparing for the physics SAT exam, because you barely get any time on that exam. Then again, I wouldn't really recommend taking that exam anyway. I just feel that it's really unfair. I've had to tutor a few students for it, and I don't actually know how they did, but still, I feel it's unfair, even if the potential points you can earn actually exceed the maximum possible score. I think, what was it? I think they expect you to do every problem within like 35 to 45 seconds, if I remember correctly, and they don't give you a formula sheet. They expect you to have all your formulas memorized, and more than that, they pretty much expect you to know some shortcut formulas in addition to the basic formulas, because that's the only way that you're getting those problems done that quickly. I mean, look at all the work that I'm putting into these. A problem like this one that we just did, they would actually put it on there and expect you to solve it in 35 to 45 seconds or less. Some people will argue that no, you have more time for these problems because a bunch of the other problems are quick problems that can be solved in like 10 seconds, but I don't know about that. Anyway, let me look for another problem worth considering. This one might be good, and I need a new stack of paper. Hold on. Where did I put that thing? Oh, there it is. I came somewhat prepared. I don't want to pull all of these out because then I'm going to have no place to store them. Let me just pull out, like, yeah, that should be a good stack right there. Let me put this away. I'll be right back. Alright, let's see what I can do with these. So we have a 12-gram bullet is fired horizontally into a 100-gram wooden block that is initially at rest on a frictionless horizontal surface and connected to a spring having spring constant 150 newtons per meter. The bullet becomes embedded in the block. If the bullet block system compresses the spring by a maximum of 80 centimeters, what was the speed of the bullet at impact with the block? So, again, a different kind of ballistic pendulum, a sort of improvised version of the ballistic pendulum, which is actually not a bad idea as long as you can guarantee that the bullet doesn't pierce through the block and then go, like, past the spring. Let's see, 12 grams for the mass of the bullet. Gets fired into a 100-gram wooden block. 100 grams. Is that visible on the screen? Yes, it is. Block is initially at rest on a frictionless horizontal surface. What else? Lost my place. And connected to a spring having a spring constant of 150 newtons per meter. So, frictionless surface connected to a spring of constant 150 newtons per meter. It's been a while since we've seen springs. Well, maybe it hasn't been a while for some of you. I guess it depends on what course you're taking and what order topics are being covered. Let's see. The bullet becomes embedded in the block if the bullet block system compresses the spring by a maximum of 80 centimeters. What was the speed of the bullet at impact with the block? So, sometime later, the block with the bullet inside of it compresses the spring 80 centimeters. And at that point, of course, we can assume that it comes to rest before it's about to get flung back to the left by the spring pushing back out. What was the speed of the bullet at impact with the block? If the compression distance is 80 centimeters, so I'm going to say delta x equals 80 centimeters, which I'm going to convert to meters because we are given the spring constant in newtons per meter. And I think I might have to convert the masses to kilograms as well. Yeah, I'm going to have to convert those to kilograms because I'm going to need them to calculate kinetic energy. If I don't plug in kilograms, then I'm not going to get joules, and if I don't get joules, then it's just going to mess up my units when calculating spring potential energy. So going with standard units this time. Did they say anything else about this? No, they did not. Okay. Let's go ahead and see what we can do then. So first step is a collision step. Is momentum conserved during the collision, at least in the horizontal direction? I know vertically gravity is going to have an influence on the bullet, like we've said with previous problems, but horizontally, is the net force external in the x direction at least? Is it 0? Well, let's see. There's no mention of air resistance, and there is no friction acting horizontally on the block. The only horizontal forces left during the collision would be the force that the bullet applies on the block and the reaction that the block applies back on the bullet. So we're good to go because those are internal forces. So net force external is indeed 0, at least in the x direction, which is good enough for this type of problem. Then we can say, I'm just going to call them M1 and M2. So M1 V1 initial plus M2 V2 initial equals, well, they come together, so it's going to be M1 V final plus M2 V final, or M1 plus M2 all times V final. Okay, so that's going to be 0.012 kilograms times whatever V1 initial is, plus 0.1 times, well, that's going to be 0, it's initially at rest, equals 0.112. If I add 100 to 12, 112 grams is 0.112 kilograms times V final. Air quotes on final because there's a second stage here. So then in the second stage we've got conservation of energy. Can we justify conservation of energy? Is the non-conservative work equal to 0? Well, let's see. So we've got gravity and normal force. Force of gravity is conservative, so we don't have to worry about it. The normal force is going to be pointing straight up this whole time while the block and bullet move horizontally, so that's going to be a 90-degree angle between the normal force and the displacement, so the normal force doesn't do any work. So that's not going to be a problem. There's no friction because we were told it was a frictionless surface, so we don't have to worry about that. No air resistance either. That only leaves the spring force, and the spring force is a conservative force. Conservative forces: gravity, electricity, magnetism, and springs. And even with springs, they have to be springs that obey Hooke's law, not just any random spring. So yes, our non-conservative work is 0, which means we can apply conservation of mechanical energy. Mechanical energy before spring compression equals mechanical energy after spring compression. Note that the mechanical energy is most certainly not conserved during the collision process because, I mean, the bullet burrowing into the block, that deformation creates friction and heat, so that energy is no longer in the form of mechanical energy. It's lost in the form of heat. Although heat is technically still a kind of kinetic energy, but that's getting into like thermodynamics territory, and we don't need to think about that. Anyway, was there anything else I wanted to say before writing the equation? I don't think so. Yeah, let's just equation away. So, where do I want to start this? I guess I'll do it down here. So I'll do, what was the total mass of the bulletin block? 0.112. So I'm going to do 1/2 times 0.112 times V final, quote unquote, squared, plus, at this point the spring is uncompressed, so plus no spring potential energy and no gravitational potential energy. I mean, even if you were to assume some sort of gravitational potential energy, if you assume this setup is on some table that's at some height above the ground, it doesn't matter because you're at the same height above the ground in the end, so whatever MGH you put in this side of the equation, it'll cancel out on the other side of the equation, since the M, the G, and the H will be the same on both sides. Anyway, so that's all good. Equals, on the right hand side, 0 kinetic energy plus 1/2 kx squared. So 1/2 times 150 times 0.8 squared plus, again, I've set the potential energy on this table to 0, but whatever you set it to, it'll be the same on both sides, and it'll cancel out anyway. Let's see, the halves cancel out, which is good because we don't have to deal with the fractions. Divide by 0.112 and we're good to go. Oh, and take the square root, of course. So 150 times 0.8 squared is 96, divided by 0.112 is 857.1428571. If we take the square root of that, I'm getting V final, quote unquote, is 29.277. I'm going to round that to 29.28 meters per second. Now that we know this, we can go back and plug it into there. So I've got 0.112 times 29.28 equals a crazy number, divide by 0.012, and I'm left with 273.28. So V1 initial is 273.28, which is a pretty reasonable initial speed for a bullet. All right, and I guess that'll be it for tonight. If you like what you see here, then make sure you show up in case you want to ask your questions live. It doesn't have to be physics. I can do math and chemistry as well. Well, some math. I'm going to teach myself statistics eventually. I'm working on it, but I'm mostly a calculus guy. And let me think. What else did I want to say? I'm probably going to focus on physics for the most part for the next several weeks, just because a majority of my students are doing physics and they've got the AP Physics exams coming up. So that's probably going to be my focus most of the time, but even so, feel free to ask questions for chemistry and math as well if you have them. If you happen to show up and you're free to come here on a Friday. If not, then I'll just continue doing what I'm doing, and maybe in the summer I'll change it up and cycle through my different subjects. I'm still not entirely sure what I'm going to do if I don't have people coming in asking questions, but I'll come up with something. Anyway, that's enough of me rambling. Hopefully this has been helpful to you at whatever point you end up finding it, and I don't know what else to say. I guess that just means that I have nothing else to say. Anyway, take care. I'll be back with another one of these next week. Might be doing some more rotational dynamics stuff, or I might end up actually doing some electricity and magnetism, because I have a student who's doing that stuff too. So I'll have to spend some time and figure out what exactly I want to do next time, but whatever I end up doing next time, hopefully it'll be relevant to you, and yeah, take care, and I'll be back next week.